All right. So I'd like to talk a little bit today about parsing a certain kind of associative operator using an LL grammar. So we've been talking about recursive descent parsers in my class. Recursive descent parsers are kind of the only ones that really make sense to write by hand. Um, Recursive descent parsers have a nice intuitive structure where the recursion and the programming very clearly matches up with the grammatical productions in a way that I think makes a lot of intuitive sense. So I'm not going to cover all of LL parsing here, but I will talk about a specific issue that comes up with LL parsing that's relevant to one of the projects in my class. So just to give kind of the sort of very high level kind of introductory overview, when we say an operator associates to the left, we mean that if we have an expression like 10 minus 2 minus 2, that's interpreted as 10 minus 2, quantity, minus 2, which is the right way to interpret this if you've taken sort of the grade school math, right? Um, Rather than the incorrect way of parsing it as 10 quantity minus the whole quantity of 2 minus 2, which would then give you 0, right? So you'd get 10 back. The correct answer is 10 minus 2, so 8 minus 2, right? So you kind of eagerly do the minus in the sort of traditional math interpretation that you'd see in everyday life. And most of our typical arithmetic operators associate to the left. But the issue is that LL parsers really don't make this very natural. And so there's kind of a hack that we can employ. And so I'm going to kind of mess around with kind of coding up the hack and discussing kind of how you would get through it. But just to kind of illustrate what the issue is, so let's look at a grammar. So let's say you've got something like this. So you've got, say, E produces E minus N or N, where N is a number. And so basically, this produces these long chains of, so an example expression would be something like 20 minus 10 minus 2 minus 1 would be an example, right? And we could write out a derivation. In this case, it would be E, and then you'd expand E to E minus N, and then we go to E minus N minus N, and then we go to E minus N minus N minus N, and then we'd start to ground all of these things. And eventually we'd get to 20 minus 10 minus 2 minus 1. Um, the thing that's nice about this is that if we read out the parse tree here, we're basically saying that eventually this in here is going to get matched up with this 1. And so we're saying it's really like this quantity minus 1. This quantity here, the 20 minus 10 minus 2, is associated with this E. Just not reading off the derivation, right? So there's this skill we talked about of being able to take a derivation, turn it into a parse tree. So that's kind of what I'm doing here on the fly. But then, of course, there's some more. So as we start to add these extra E's, well, then now that becomes this next layer here gives us the 20 minus 10 quantity minus 2. And then eventually well, here's the answer, right? So the whole thing is just this. And that's the proper way to parse it. But this left recursion here is a problem. This is not an LLK grammar, so we can't write a recursive descent parser for this. You could use an LR parser, for example, like a parser generator will handle this no problem. And that's a big reason why in practice you might really want to use an LR parser. Um, but, you know, we're not really going to cover LR parsing in detail in my class. I just think it's not really the right focus, at least for students at my level, and not really something I have a lot of expertise in explaining anyway. if you're interested in that, I'll let you go dig up some other material on LR parsing. We'll talk a few slides about it in my class, and so I'll post some slides a little bit as well. Generally, the idea is that you use a sort of a shift reduce style parser. But coming up with the parser tables is rather complicated. So, we want to stick with this intuitive style of being able to write these recursive descent parsers. And the issue is you can't write a recursive descent parser for this thing here. And the reason is when you see an E, the first thing you need to do is you need to recognize another E. And so what that means is that you have to translate it into basically this infinite loop right here. And that's no good. You really don't want that, right? And this grammar has other reasons why it's not LLK as well. We could kind of go through and talk about things like the first and follow sets and things. But from a programming perspective, this is the issue, is that left recursion in the grammar translates to infinite loops. And so you just can't write grammars that are left recursive, even though this grammar will give us the proper parse tree that we want, and thus the proper syntax tree, since basically a syntax tree is just kind of a filtered version, kind of a massaged version of the parse tree. Not that there's a huge value in differentiating them. Okay, so now let's talk about how we might try to rewrite the grammar. So you might say, okay, well, what if we put the recursion on the right? That's kind of a simple fix that like kind of recognizes the same set of strings, right? So let's say I do E. So this is my second try. So E is going to produce maybe either an N or so let's do N minus E or N. And then N is just a number as before. And maybe we can even just say it's like a number. Num minus E or num. Okay, so for this one, well, here we could write it, and it's natural. So I'm going to use the same trick I showed before. So we're going to say parse E. And we're going to take a stream as input, and then I'm going to match on the stream. And I need to consume a number, first of all. So I need the first thing in the stream to be a number. We need to say what this stream is. I've kind of left it a little bit vague in my various examples. It's a list of tokens. So in this case, maybe we can come up with a little example, which is int 3, and then minus, and then int 5, and then minus int 1. So that'll be our example. So if we match the stream, and we see, now this grammar is not LL1, but it is LLK, because if I look at the first two things, and if I see a num, so if I see an int with some value v, and then if I see a minus, then I know I'm in this first production here. And the next thing I need to do is to parse an E. So I'm going to recognize this as one of my match cases. And here I'm going to call that rest. So here I saw an integer and a minus. I need to parse an E. And I'm going to do that using recursion, and there's no problem here. So here I'm going to say, so first, assume parse E returns a 2-element list, which is basically AST and rest, where AST is the returned AST, the abstract syntax tree, the thing that we want as a result of our parsing, and RST is the rest of the input. And this is just this way of doing sort of immutable stream-based programming. We're technically using something like a monad here, right? There's a state monad of the stream if you're somebody who's like a Haskeller. But if none of that made sense to you, basically the answer is just instead of mutating the stream by having some global or mutable notion of the current input in the stream, we're just going to pass around a list, which is the rest of the stream that we're sort of consuming. And then as we pull characters off that list, it's our responsibility to return the rest of the stream so that the person who called us knows how many tokens we take off. And so we're going to do that by returning all these parse functions. Will return a 2-element list just because we want to return multiple values. We want to return the AST that got parsed, and we want to return the rest of the stream as well. But in any case, we're here, we've recognized the int, and we've seen a minus, and now we had better see an e. And so we're going to call parse e, and parse e, its job, the recursive call, will go parse this for us, and it will return to us whatever syntax tree it got from parsing e right here, and also the rest of the stream. And so I'm going to use match to get at that. So I'm going to say match parse e of the rest of the stream we got from taking off the first two things. So we pull this off, and now we've got e to start with. So we're going to match parse e, and it's going to give us parsed e, which is the syntax tree that we got from parsing this thing right here, and also a rest of the stream. I'm going to call it rest plus to syntactically distinguish it from RST right here. And then here I'm going to say, so now I've got a num, I've got an e, I'm going to just make a minus now. And I'm going to say my result is going to be, it's going to be a 2-element list. This is going to be the returned, I'm going to fill this in later. It's going to be the returned AST, and this is going to be the new rest of the list, which in this case is going to be RST plus. The thing that I got from parsing E finally gave me back a rest of the list from when it was done parsing. So I'm going to call that RST plus, and then let's fill this in now. So it is a minus. I'm going to write it in this kind of style here where I use the sort of scheme style, which is to put the operator in the front and sort of do this prefix style. And now I can say the actual number here is this value v, and I've got parsed e right here as well. And that's going to be my result. And the other case is that I see an integer and then something else. So I see an int, and that is my first thing, and then anything else, and it's a rest. And ooh, I made a mistake up here. This is a list. It should be a list. But right now, this is actually a pattern that matches a 3-element list, whose first element is an int with a v, whose second element is the symbol minus. So I actually made a mistake there as well. I called it minus up here. So that was a mistake. And then this third element, it's not really a third element. It should be whatever is the rest of the list. So I can do that by doing the ... which is basically the cleany star of the previous argument. And that says match 0 or more things here, but match them as a list called rest. Okay, good. And so then here I've got rest ... So there we go. And now I want to return just v, since that's the value of parsing an int. And I want to return this rest. And I think that's what I've got. And well, now this grammar, it recognizes the same set of strings, but it doesn't parse them in the same way. So this is a problem. But first, let's just check to make sure that this works at all. So let's hit run. Okay, no syntax errors. That's good. And we'd like to see parse E on X, which is our example language. And let's see. Looks like it works fine. Yeah. I might even try adding an end of file character here, something like that, just to show us. Hit run, and then let's do parse E on example. And here we go. We get the minus of 3 quantity minus of the whole quantity 5 minus 1. And so, okay, yeah, that's no good, right? We didn't really want that. So that's too bad. But at least we're closer, and hopefully this at least gave you a refresher on how the whole idea of recursive descent works. But we need to basically take a different approach if we want to actually get this to work using an LL parser. So there's kind of a simple trick that I'm going to show you, and here's basically what the trick is. So the basic trick is to recognize that really we wrote a regular expression, which was basically that E is basically num followed by minus num star. And it's not too hard to implement this using a loop. So either a recursive function in a functional language or whatever, some other trick like that. And so here's what we're going to do. Basically, this means the result of parsing E is a list of numbers. So let's say I had something like the example here. In this case, it's this thing int3 minus int5 minus int1, right? So in this case, what I would do is I would pull out 3, 5, and 1. So let's say it's a list of numbers like 3, 5, 1. Well, then it's not too hard to write a little function that walks over this list and emits an expression of the desired structure, i.e., I guess the observation is basically if we have the list, we have the values as a list, we can then fix up the associativity post hoc. So what I mean by that is we write a function that takes, for example, 3, 5, and 1. We write a function that takes that and then just does minus 3, 5, 1 as the parentheses right here. So it's not too hard to write a function that does this. And so let's try to maybe write out what that function might be. So one thing is that it looks a lot like sort of a fold L and a fold R thing in a certain kind of a sense, right? In the sense that if we have something like x0, so if we have like cons of x0, cons of x1, cons of x2, and so on. And then the empty list. Now, then fold L, or sorry, fold R basically replaces all the cons with like an arbitrary function f and replaces this empty list with an arbitrary initializer I. And you can use that to basically write the class of primitive recursive functions over lists. That's what the sort of fold R gives you. But fold L will allow us to, sort of take these values out one at a time and walk over them. So I think we can do fold L here and get a really nice result if we use a little variant of it. So let's think a little bit about it. So let's say if I have a function here, let's write fix up, and then here's my list. And the job of fix up is to basically do this thing here. think I'm going to delete this little comment since that wasn't too insightful. And our goal, so I'm just going to try to guess at what I think it is. I think it's basically fold L of lambda, give me the next element, and give me the accumulator. And then I'm going to generate minus of, I think, the accumulator here and the next element here. And then we're going to start that with the first of list. And then we're going to fold over the rest of the lists. And I think this will work because we're starting with 3. That's going to be the initializer, and then we're going to minus 5 by that. That will become a new subordinate thing. That'll be the minus 3, 5. Then we minus the 1 to it at the end. So let's see if it works. Let's just run fix up 3, 5, 1. And yeah, I think it works fine. Fix up range 10. Yeah, looks solid. Okay, so that's our next step. So now we need to just recognize, how can we recognize a little regular expression here, right? So how do we do it? Basically, we write a little helper function. So I think what we do is we maintain a list of the nums we've seen so far, and then we look at the first character, see if it's minus. If it is, we try to parse another num, recursively call ourselves by adding that num to the accumulator. So let's try to follow that logic. I think basically our goal is to recognize this. And here's what we're going to do. We're going to say parse E, and it's going to return the same interface as always. So it's going to returns a 2-element list of parsed E and then the rest. And so we've got a stream here that's our input. So I'm going to basically consume a num. So I want to match the stream, and it had better look like an int of some number n followed by a rest. And now I'm going to call my parse e helper function on the rest here, and my list that's going to be my accumulator is going to start with n. And I think that's how it's going to go, because in both of these cases, well, because we always have a num here that starts us out. And so now I'm going to write my little helper, and I'm going to say parse e helper is going to take a stream, which is the rest of the input, and it's going to take a accumulator, and it's going to look at the stream. And if the stream begins with a minus, it's going to be followed in ooh, I made the same mistake up here. This needs to be rest ... Otherwise, it won't match as a list. Same thing here. Rest ... We're going to match that stream. And it means, so this is like the recognizes this portion. This is, we matched. Now expect a num. So in fact, this had better be an int here. So let's say it's int of n, and then a rest ... So we were able to expect that by writing the match pattern. So we look at the stream, we see a minus, we see an int n, So here, we're going to call parse e helper on the rest of the stream. And now I'm going to cons on into the accumulator. There's a thing that's happening here, which is that we're building up the list sort of front to back. So we kind of are reversing the order of the list. So at the end, when we hit the base case, we're going to have to reverse the list if we want it in the right order. And that's a very common thing with tail recursive functions when you write them. And here, the other case is, so we didn't match. Now we're done. And we're done parsing the whole E because this call to parse E helper, this is a tail call. And so the return value here, ultimately, when we don't match, this is like we couldn't find a minus. So we're in the case where we know this is actually empty. So we found something like EOF or whatever, something in the follow set of E, basically. So here we didn't match. We know we're done, but now we need to return our result. And what's our result look like? So our result is a 2-element list, which is parsed E, and that's the original thing that we tried to parse originally here, and then the rest of the list. Now, in our case, we need to produce this correctly parenthesized and associated list where all of the elements from the list come from this accumulator. Now, we already wrote this little function here, fixup. And so I think we can just call fixup on the accumulator right here. And I think that's it, except that's the return value. And we need to reverse this because we're building it up sort of front to back. So we're going to naturally end up reversing it. And then the rest is going to just be stream, because here's the case where we were looking for basically a star pattern. We realized there's no more minus to be had. We can't find a minus, which is the thing in our first set here. So it must be the case now that this star actually generates the empty string. In that case, we don't want to consume anything from the input stream, and we just want to return stream back to our caller because they're going to pull tokens from that for the rest. And so here I can just write stream. And let's see if this works, you know? Okay, so we already defined it. So let's maybe call this G. And I'll just go through. I'll rename everything. Okay, let's try it again. And then our example is named what? X. Okay, so parse G and then X. Ah, looks like it works. Excellent. And I think it works for other stuff too. So let's see. Let's add a bunch more. Minus int 12 minus int 20. Let's see, does it still work? Yeah, looks right. 3 minus 5, quantity, minus 1, quantity, minus 12, quantity, minus 20. And then we get the end of file back. So this is the basic trick. I'll kind of leave it here, but this is the hack. If you're parsing something like this with an LL parser, you really can't do it in general. I mean, you really need to be using an LR parser for this, but LR parsing is its own can of worms. I'm not really going to dedicate a ton of time to covering it in class other than showing how Yak and a few of these tools work and maybe hinting at some of the intuition for how things like LALR and stuff work. But I think we have better uses for our time. I think the recursive descent style is particularly intuitive. And so hopefully this helped with that. And then especially this trick right here of being able to recognize that you can break it down accumulate a list of all of the things that would be minused, and then fix them up to have the right associativity. That hack, in some form or another, is in a bunch of LL parsers that are trying to do this kind of arithmetic. And so, it's not LL, right? It's using things like the stack and stuff like that to affect something that's beyond the expressivity of LL. But it's a cool little programming pattern. And when I saw it, I thought it was very interesting. It was one of the first times I was studying kind of programming seriously. And it was one of the first kind of insight moments I had that you could kind of go beyond the scope of the power of this sort of regular or, context-free language of LLK type things and be able to use the stack in this manner to be able to get this sort of left associative behavior, which you really want. Okay. Please reach out to me if you have any questions. I'll write my email down here for people who aren't in my class. But if the code is useful to you, feel free to use it in your project, and I'll post the video. And I'll also post a link to the code below the video as well. All right. Thanks so much for tuning in.